Good morning, everyone. I'm excited to welcome you all today. Today, we'll be exploring the need of new approach TO atomic structure. In this presentation, we'll look at why our current understanding needs to be revised and what new ideas are emerging. We'll cover the key challenges and the innovative theories that are shaping the future of atomic science. Let's get started. Today, I want to talk about why atomic structure really matters. So, what exactly is atomic structure? Well, it describes how atoms are built, the tiny building blocks of everything around us. Atoms are made up of protons and neutrons, which form the nucleus, and electrons that orbit around it. Understanding how these particles interact is key to understanding the atom itself. Now, why is this important? Because grasping atomic structure fuels progress across so many fields: chemistry, physics, medicine, electronics, you name it. It helps us develop new materials, better medicines, and innovative technologies. Essentially, a solid understanding of atomic structure is the foundation for many scientific and technological advancements that shape our daily lives. Let's take a closer look at the current models of atomic structure. First, we have the Bohr model. Imagine electrons orbiting the nucleus in fixed paths, kind of like planets orbiting the sun. This model was quite an achievement because it explained the energy levels of hydrogen atoms and even how they emit light spectra. However, it has its limitations. It doesn't work well for more complex atoms with multiple electrons, and it overlooks quantum effects, which are crucial at the atomic level. Now, moving on to the quantum mechanical model. Instead of fixed orbits, electrons are described as existing in probability clouds or orbitals, which are defined mathematically by wave functions. This approach allows us to predict how electrons behave, understand chemical bonding, and determine the properties of materials far more accurately. But of course, this model isn't perfect either. It's quite complex to perform calculations with, and it doesn't incorporate gravity or Einstein's theory of general relativity. Overall, these models show how our understanding of the atom has evolved from simple planets to complex quantum systems, helping us unlock the deeper nature of matter. The Standard Model serves as a framework for understanding the fundamental building blocks of matter. It describes the subatomic particles, such as quarks and leptons, that make up everything around us. It also explains the forces that govern their interactions, with the exception of gravity. One of the key achievements of the Standard Model is that it has been confirmed through numerous experiments, including the discovery of the Higgs boson, which was a major milestone. However, despite its successes, the Standard Model has its limitations. It doesn't include gravity, which is a fundamental force, nor does it account for dark matter or dark energy. So, while it provides a very strong foundation, it's not a complete picture of the universe. This sets the stage for us to explore what's missing and what future theories might address. Let's start by looking at some of the limitations of our current models. First, dark matter and dark energy make up about 95% of the universe, yet our existing atomic models simply can't explain what they are or how they work. This is a huge gap in our understanding. Next, there's quantum gravity. We haven't yet developed a successful theory that combines quantum mechanics, which governs atoms and subatomic particles, with general relativity, which explains gravity on a large scale. It's one of the biggest challenges in physics. Then we have the issue of complexity. Quantum mechanics is incredibly abstract and mathematically challenging, making it difficult to apply to larger, more complex systems. This limits how practically we can use quantum theory in real-world applications. Moving on to some specific gaps in our understanding, the measurement problem is particularly intriguing. Why do particles behave differently when they are observed? Our current models don't fully explain this phenomenon, and it remains one of the fundamental mysteries of quantum physics. Finally, high-temperature superconductivity, or HTS, is another area where we lack clarity. We know some materials can conduct electricity without resistance at higher temperatures, but why this happens in some materials and not others is still not fully understood. All these points highlight the ongoing challenges we face in advancing physics, and understanding these limitations is crucial as we push the boundaries of knowledge. So, why do we really need a new approach? Well, one key reason is solving mysteries like dark matter and the strange behavior of black holes. A new model could give us a better explanation for these cosmic phenomena, helping us understand the universe on a much deeper level. Another important point is unification. Right now, we have different theories for different forces: gravity, electromagnetism, and others. But we need a theory that can bring all these forces together into one coherent framework. That would be a huge step forward in our understanding of physics. And then there's simplification. Having a clearer, less complex model could make atomic science more accessible and practical for everyone. It would help us apply scientific knowledge more effectively, opening up new possibilities for research and innovation. Overall, these reasons highlight why a fresh perspective is essential for advancing our understanding of the universe and making science more unified and accessible. Now, let's explore the potential benefits of this new approach. First, there's the possibility of a scientific breakthrough. This could help us answer some of the biggest questions in physics, like understanding what causes gravity at the quantum level. Imagine finally unlocking how the tiniest particles influence the force that keeps planets and stars in motion. Next, there are exciting technological advances. Improving our atomic models could lead to innovations in areas like quantum computing, energy production, and new materials. For example, we might develop more efficient solar panels or faster, more powerful computer chips that transform how we live and work. Finally, this approach could deepen our understanding of the universe itself. It might reveal how atoms behave under extreme conditions, such as inside stars, helping us learn more about the cosmos and the fundamental forces at play. Overall, these benefits show how pushing the boundaries of our knowledge can lead to groundbreaking discoveries and practical innovations that shape the future. Now, let's look at some of the current efforts towards developing new approaches in understanding the universe. One of the most intriguing ideas is string theory. The core idea here is that particles are not just tiny points, but actually tiny vibrating strings. This concept is fascinating because it offers the potential to unify all the fundamental forces and also to explain atomic behavior at the smallest scales. It's like trying to find a single, elegant framework that ties everything together. Another promising approach is loop quantum gravity. The idea behind this is that space and time themselves are quantized, meaning they're made up of tiny, discrete packets. Think of it as space and time being like pixels on a screen, fundamental units that make up the fabric of our universe. The promise here is that this approach might bridge the gap between quantum mechanics and gravity, two areas that have traditionally been hard to reconcile. To explore these ideas further, scientists are conducting experiments using advanced tools like particle accelerators, CERN being a prime example, and powerful telescopes. These instruments help us test and refine these theories by observing atoms and particles in ways we couldn't before. It's an exciting time as we push the boundaries of our understanding through both innovative ideas and cutting-edge experiments. All right, let's talk about the challenges ahead. One major difficulty we face is creating a new model that can effectively merge theories across vastly different scales. We're talking from tiny atoms, which are incredibly small, to huge galaxies that span millions of light years. This scale difference makes it really complex to develop a unified framework. Then there's the challenge of testing these new ideas. Advanced technology is needed to prove or disprove them, and developing this technology can take years. We're in it for the long haul, and patience is key. Finally, acceptance is another hurdle. Scientists need to be open-minded and willing to rethink long-held beliefs. Progress often requires challenging the status quo, and that can be difficult but is essential for breakthroughs. All these challenges, creating a comprehensive model, technological development, and shifting mindsets, are interconnected, but overcoming them is crucial as we push the boundaries of our understanding. So, as we wrap up, I want to emphasize that while our current models have taken us a long way in understanding atomic structure, they do have their limitations. They're powerful tools, but they don't tell the entire story. And that's the exciting part. There's still so much we don't know, and that opens the door for new discoveries. In fact, the next big breakthrough in atomic science could come from any one of us. Whether you're a student, a researcher, or just a curious mind, your ideas and questions could lead to the next big insight. So I encourage all of you to stay curious and to keep exploring. Science is a collective effort, and shaping the future depends on our willingness to ask questions and venture into the unknown. Thank you very much for your attention and engagement today.